Okay, in this video I'd like to cover Chapter 2, Section 1 in our Algebra 2 class. We are revisiting some information from Algebra 1, and I wanted to make sure that we're all on the same page. So in the video today we're going to talk a little bit about the differences between functions and relations, and here are some vocabulary terms that we plan on covering in this video as well. So hopefully you become familiar with domain and range, as well as independent and dependent variables. We'll talk a little bit about the vertical line test and again what the difference between a function and a relation is. So in general, one of the goals in mathematics is to describe relationships between sets of numbers, and we do that to understand a situation better, and really most of us recognize this as problem solving. So if we have a relationship between a set of numbers, we can likely apply mathematical rules to solve the problem. So simply put, we would say that a relation is a set of pairs of input and output values. If you provide an input to a relation, the relation will describe the output value. The domain of a relation is the set of inputs, also known as the independent variables, or x-coordinates of the ordered pairs. So every relation has a domain, and the domain is what we would consider our input values. What values can we place into the relation and calculate a result from them? Now, the results are called the range, and the range is the set of outputs. So if the range is the set of output values, these are also known as dependent variables. And they would be identified by the y-coordinates of an ordered pair. So in this class we'll talk about 4 different methods or 4 different ways to represent relations. They're listed down below here. Hopefully you recognize these. These are ordered pairs, which show a relationship between input and output values. You could also call these coordinates as well, and that would be just fine for me. But again, we have a series of input values. If I input the number 3, for example, I get an output value of -1. If I input a number 4, I also get an output of -1. If I input a number 4 again, I might get an output of 3. So input, output, domain on the left, range on the right. Now similarly, we have this option over here to represent a relation. This one's called a mapping diagram. And rather than list our input and outputs as an ordered pair, we have a collection of input values, or our domain on the left in this case, and a collection of output or range values on the right. And these arrows are simply used to map or illustrate the relation between the input and the output values. For example, if you select 4 again, that maps to -1, but 4 also maps to 3. These two show the same data. In this third option, we would simply call this a table. Some would call it a table of data. Some call it a table of values. Either way, it looks quite similar to our mapping diagram and or the ordered pairs. In fact, I think it looks a lot like an ordered pair because within each row we have the same ordered pairs that we had listed originally. It's just a slightly different way of reporting or indicating the relations. Now finally we have our graph. This is the 4th way to represent a relation, and if you'll notice, we've simply placed the ordered pairs or coordinates and the results from our table of data or mapping diagram to their appropriate locations on the graph. Of course, here is -3, 4. This coordinate is 4, 3, and so on. So in this example, I want you to think about what are the parts of this graph and what might they represent. In other words, can you pause the video in a moment and identify where the input and the output values are located? What's the domain and range of this function? And of this relation, and what might this particular graph represent. We have more data in this graph than the last example with the descriptions on our horizontal and vertical axes. And I want you just to think a minute about where the domain and range exist and what this graph might represent. Please pause the video now and resume playback in a moment to check your work. So the first thing that I would note is that our domain or input values show up along the x-axis. Earlier we said that these relate to the x-coordinates. And our range or outputs show up along the y-axis. So we might say that the domain of this relation is time and the range of our function is height, but we can actually be more specific than that. We can actually list the x values and we can list the y values that exist in this particular relation, and we can have a list of both the domain and range values. Let's pause the video now and again try to identify the actual domain and range values for this particular relation. So here I've just listed the x values, or the inputs that were used to generate output values. So the inputs in this case were 0, 4, 8, 12, and 16. Not because those were the numbers that were listed on the x-axis, but because those numbers actually correspond to data points that are in the graph. Now similarly, I've identified the y-coordinates, or the range values, or the outputs for this particular function. And I had to make an educated guess for some of these because the graph isn't so clear. But we did have a y value at approximately 10,000, another y value that was a little bit less than that, so I called it 9,750, 8,900, 7,750, and 5,900. Those are the x and the y coordinates, the inputs and the outputs for this particular graph. And we could also reorganize these data points as an ordered pair, a mapping diagram, or a table. I'm not going to take the time to do that right now, but this is something that we can discuss further in class. Now with some further analysis, we might find that this is the equation that produced these coordinates. And the question that we asked earlier is, what might this represent? Well, even if you didn't know the equation, you might have a guess in mind, but with the equation it might become a little bit more clear. But to me it looks like this relation represents the time as an input and the height as an output, and this is probably an object that's falling, that's in free fall. So after a certain amount of time, after an object is let go, we can determine how high in the air that object is. Maybe this is a skydiver or a meteor or something like that that's falling from the sky. It's starting at about 10,000 feet, and we can track its height on its way down as we monitor the amount of time that passes. So if I describe that with this phrase here, the height of a falling object relative to time, that kind of implies that time was our input and the height is our output. We can calculate the height of a falling object based on, or relative to, the time that we provide to the equation. Now in example 2, we have another example of a relation. We're talking about the monthly average water temperature in the Gulf of Mexico in Key West, Florida. In January, the temperature ended up being an average of 69 degrees. In February, it was 70, March 75, and in April 78 degrees. How can we represent this relation in 4 different ways? What are the 4 ways to represent a relation? Well, again, we could indicate this relation with a set of ordered pairs, with a mapping diagram, a table, or a graph. Now, we have to be a little bit careful with data like this, especially if we were to try to report this as an ordered pair. Typically, ordered pairs are combinations of 2 numbers, but we only have one set of numbers, or one numerical value for each data point. So a lot of times what we'll do is we'll convert this text description and place that as replace that with a numerical value. So as an example, we might say that we have the coordinate 1 and 69 for January and 69 degrees. We might have the coordinate 2, 70, 375, and of course 478. If we had more room, I might ask you to draw a mapping diagram, a table, and/or a graph of this data, but we ran out of space, and maybe I'll leave that up to you as an exercise in class. If you'd like clarification on each of those options, please let me know. Now moving on, relations are nice. We show how input and output values can be connected using the 4 methods above, but there are special relations that we're going to study in this class called functions. Now a function is a relation, it's a special type of relation, in which each element of the domain, or inputs, corresponds with exactly one element of the range, or outputs. So if each input corresponds to exactly one output, that means that functions are kind of nice, and I put nice in quotes here because that's a bit subjective, but functions are nice because only one x-value solution, there will only be one x-value solution to each y-value of a given problem, or each identified y-value of a given problem. Now that may sound strange at first or a bit vague, but I'd like to clarify that claim here with just a few examples. First off, we have a set of relations. I know that they're relations because these are all representations based on the format that we've seen already. Here's a mapping diagram, and the question becomes whether or not these are, or this is an example of a function. It's a relation, yes, but is it a function? Well, in order for it to be a function, each element of the domain has to map to or correspond to exactly one element in the range. So sometimes I'll almost cover up this range. I'll kind of forget about what's over here, and I'll focus only on the arrows that are drawn from the domain. And I'll ask myself, does number 3, sorry about that, does the number 3 map to or point to only or exactly one element in the range? -3 does that. Does the number 0 map to or point to exactly one element? Yes. Does number 4? Yes. Each one of these inputs points to exactly one output. Doesn't matter what the range is, but I do know that every input produces exactly one output. So again, each input corresponds to exactly one output in this case. In the next example, it's a little bit harder to see, but we have an input of 4 and it maps to -1. We have an input of 8 and it maps or corresponds to 6. 1 corresponds to -1, 6 corresponds to 6, and 4 corresponds to 1. At first glance, that looks okay. Each input maps to an output, but upon closer inspection, you might recognize, well, we had an input of 4 at the beginning, and input 4 mapped or corresponded to -1, but now 4 produces an output of +1, and that's a problem. That's where the confusion lies, and that's where functions become helpful. If this was truly a function, there wouldn't be the confusion. Where does 4 map to? Well, some would say that it maps to -1, some would say that it maps to +1, others would say that it maps to both, and in either case, that's a problem for our special relations called functions. And we would say that no, the input 4 does not map to exactly one function. 4 is the culprit here. Now some of you may have noticed that 6 was common, but recall that this 6 in this position is an output in this case, and that's okay. We can have different inputs mapping to the same output. That's not a violation of our definition of a function. The problem that we have is that we don't want that ambiguity or confusion to arise from our inputs pointing to the outputs. If I give you an input, you should be able to tell me precisely what the output is with no confusion or inaccuracy. Now in this third example, we have another mapping diagram, and I want you to think about this one on your own. Does this relation represent a function? Does each input map to exactly one output? Pause the video now and provide your response. Resume playback in a moment to check your work. And we could say something like this: no, because the input 2 does not correspond to exactly one output. If I provide an input of 2, it actually could land in 2 different positions, and that's a violation of our definition of a function. Now, with those examples in mind, and perhaps us coming back to the example on the prior page, I'm going to talk real quick about a visual way to check for functions versus relations. Back here we said that this example is a graph display of a relation, but this particular example and all of the data in this group does not represent a function, because here again, if I consider the input, in this case 4, we actually have 4 that points or maps to 2 different outputs. And if I choose 4 on the x-axis, or if I choose 4 from our table of data, I don't know if 4 is pointing to -1 or +3. I can't really choose both simultaneously. I have to pick one or the other. So because these 2 inputs map to 2 different outputs, we end up generating a pair of data points that are essentially stacked on top of one another, and this is what we call a vertical line, when we create a line vertically, of course. And this corresponds to what we call the vertical line test. If you have a graph for which you can draw a vertical line through 2 data points on your graph, then that means that your relation is not a function. So because of this, I might say that this is a vertical line test fail. Therefore, this is not a function. It's still a relation, of course, but it is no longer a special relation that we would call a function. In this graph, there was no vertical line that I could draw that would go through 2 points simultaneously. So this one would be a vertical line test pass. Therefore, this graph does represent a function. Now let's try to finish out the video with a couple more examples. And I kind of gave you a freebie on the fill in the blanks portion of the notes here. An equation that represents an output value in terms of an input value can be written as a rule, a mathematical rule. And while we're used to seeing rules written as an equation, maybe like this, we can also use what's called function notation. Now, if you look closely at the differences between an equation and a notation, or the similarities, first off, you'll notice that the right side of the expression looks exactly the same. We have 3x plus 2 on the right side. Now, normally in an equation, we identify the output variable as a single letter, but in function notation, we give the name of a function and we identify the input values, what variable might represent the input values, in this case, x. So while both mean the same thing and they're written just slightly different, in math class we use different terms or instructions to ask students to evaluate a result. So if I had an equation written and I wanted to know what the equation was equal to when x is equal to 2, I might have to write this entire phrase. Evaluate the equation for x equals 2. And we could do that. We could say that y is equal to 3 times 2 plus 2. And that would be 6 plus 2, or in other words, y is equal to 8. In function notation, on the other hand, we don't need to go through the trouble of describing the math altogether. We can simply provide our instructions with this short phrase. This indicates to use the function that we named f and to replace the letter x with the number 2 and evaluate. So quite simply, we're taking the number 3 times 2, and we're adding 2 to it. Now, out of habit, a lot of times when I'm working with equations, I'll use a times symbol for multiplication, but when using function notation, I'll almost always replace the letter x with a parenthesis and a number inside. That's just one of the things that I do, and that may or may not be helpful when I allow you to use calculators to simplify a result. For example, if I wrote 3 parentheses 2 plus 2 on this phrase, and I go to the calculators that we have available in our classroom, I could do the same thing. And if I could repeat the expression from paper in this calculator precisely, in other words, if I can get the calculator to look like the expression that I wrote on paper, then I can trust that this calculator will follow the order of operations correctly, and it will produce an answer that we're looking for. So I think I've done that here. I've got the expression written in the calculator that matches the expression on paper precisely. Just the right side, mind you, not the left side of the equation. And we do get an answer of 8. Looking back at the calculator, you'll see that its format changed just a little bit, and it matches more alike with what we had written on the left-hand side. And that's okay. That's just a feature of the calculator. I know that I typed in this expression directly, and I got the result of 8. So if calculators are permitted on a test or a quiz or on a practice set of problems, this is an amount of work that I feel is appropriate to show if you're using the calculator, whereas if you're not permitted to use a calculator and you have to do the work by hand, we might show something like this. So let's get some practice with the calculator. Here's another example of a function. Notice we've defined the function f of x, and we're being asked to evaluate f at 4. So what's that going to look like? Well, f of 4 would be equal to 17 times 4 plus 3. And if I can make my calculator match this expression, then we're going to be in good shape. So I'll come back here and I'll type 17 parentheses 4, close the parentheses, plus 3, and press enter, and we get a result of 71. Here again, if calculators are permitted, then this would be a fair amount of work to show. Notice, not only am I showing the math or the setup for the calculator and the result, but I'm also including the function notation as well. I would like to see that you understand that all three of these expressions are related to one another. Now in this last example, we'll do the same thing. F of negative 1 is equal to a negative sign in front of a fraction with 12 times negative 1 in the top in the numerator and 5 in the denominator. So let's see if we can create that expression in our calculator too. Now there is a difference between a negative sign and a minus sign in these calculators. If you want a negative symbol, make sure that you press this key here. That's the negative sign. And to create a fraction, you may notice that there is a tiny fraction button here next to the division sign. To access that command, we press the Control and Divide key. Now we have an empty fraction that we can fill in. And, whoops, cursor moved there. Now we can write 12 times negative 1 with the parentheses over 5. And I'm just using the up, down, and left and right directional arrows to move to different positions in the expression. So a quick check, does what I have in the calculator match what I had written on paper? Yep, and since I was happy with what I had written in paper, I know that I can trust what I get from the calculator, so I'll go ahead and press enter here, and that reduces to 12/5. This calculator will produce exact answers in fractional form, by default if it can. However, if you're interested in the decimal value, we can quickly obtain that as well. Instead of just pressing enter at the end of a computation, if you press Control Enter, it will complete that computation and produce a decimal result. So depending on how the question's worded or what we're looking for, we may want the decimals, we may want the exact answer. In this case, either one is correct. Just check your instructions to make sure that, that you understand what's being asked of you. Now finally, one more real-world example, and then we'll call it a day on this lesson. We are in a position where we're considering renting a car from two different companies. We're going to go on a road trip. The Proxy car rental company charges 32 cents a mile plus an $18 surcharge, and the Your Pal rental company charges $36 a mile, but only a 36 cents per mile, but only a $12 surcharge. So we need to write a function for both the Proxy and the Your Pal situation, and then we've got to decide which one works best for an 820-mile round trip. So in question A, with some practice, you'll recognize that the charge per mile is going to be our what we call the slope of our linear equation, and we'll use that as the value that multiplies by our independent variable. And then the $18 and $20 surcharges, those will act as as what we would call our y-intercept, or the initial cost or offset to the linear equation. So in question A, we might write something like this, that the function f of x, which represents our total cost, would be, let's see here, for the proxy company, we might use something like this, 0.32x plus 18. So 32 cents per mile, where x is the number of miles that you drive, and 18 is the standard cost just for executing the rental. For part B, I'm going to switch things up a little bit. I'm going to use g of x this time. So g evaluated at x, and I'm going to call this one 0.36x plus 12. This is for the Your Pal company. Now here's a benefit for using function notation. We can give different names to these functions. We can use different letters to represent different functions. And so later, if we start computing with those functions, we should be able to tell the difference. Both of these are going to be used to determine the cost for an 820-mile trip. But if I write f of 20, I know how to compute that, and I should recognize that f represents, in this case, our proxy car rental company cost, and g is going to be the Your Pal rental company cost. So if we evaluate these, this would be 0.32 times 820 plus 18, and 0.36 times 820 plus 12. And now we can go to the calculators and compute those results. Now, one last thing before I switch over to the calculator. I'm not sure if you heard the way I was describing this, but when I see this phrase f parentheses 820, I'm actually saying to myself and saying out loud f of 820. And that's just the language that we've adopted in most math classes. We're not saying that f is multiplying by 820. I know it may look like that because of the parentheses here. And in this example, we are going to multiply 0.32 times 820. We're not actually multiplying the letter f times 820. This is simply the notation that's been adopted giving us the instruction. And so to distinguish the difference, you'll hear me say f of 820, or in the next example, g of 820. And again, we're not multiplying, we're just using that as our instructions. So when I switch over to the calculator, I'll do something like this, 0.32 times 820 plus 18, so it's a smaller mileage rate but a higher initial cost, and we'll compare that to 0.36 times 820 plus 12, so a higher mileage rate but a lower initial cost. And now we can fairly quickly tell which one's the better deal. We have to spend $280.40 for this rental, but $307.20 for the other. So if I had to choose, it looks like the proxy car rental is the way to go. So I know this video was a little bit lengthy. Thank you for sticking it out, especially for those of you that weren't in class on this Tuesday, and hopefully this gets you caught up a little bit for what you missed. If you have questions, please let me know. Reach out to me, and we'll talk to you later in class. Thanks for watching.